first, I wish Happy Saraswati Puja and Happy Republic Day. This Republic Day, let's promise to build a country that will be ideal place to thrive for next generation. Then I wish Happy Saraswati Puja. I pray to God for your a prosperous life and may you find all the delight of the life and may all your dreams come true. Okay? So again I wish Happy Saraswati Puja and Happy Republic Day. Welcome back. Today I will actually discuss inner product space. In my previous video I had discussed inner product space elaborately, obviously. But today I will discuss this space again because actually inner product space is very important for higher study. And today's goal of this lecture, at first I will see one question which had come in CSIR net exam based on this space. Then I will say one nice concept. If VBA inner product space and VI be a basis, then always I will get a matrix A which is symmetric. In my previous video I have discussed what is the positive definite matrix in inner product space. Always I will get one matrix which is positive definite, and the actual definition of inner product is a bilinear form is inner product when this is the positive definite. That means by inner product we can always construct a symmetric matrix with the basis, and today I will discuss this concept easily because I have told you inner product space is very important for higher study. Question which had come 26 November 2020 exam. The question is VBA vector space in R3 which is non-zero vector space, and defined a linear transformation T from R3 to R3 by T of x equal to x minus 2 times x dot v over v dot v times v, where x dot y obviously denote the standard inner product on R3. Then the option is the eigenvalue of t is plus 1 and minus 1. Option 2, the determinant of t is minus 1. Option 3, trace of t is plus 1. And option 4, t is distance preserving. For this, notice here the linear transformation is denoted as tx equal to x times x minus 2 times x dot v over v dot v times v. Here we have to find eigenvalue of this linear transformation, determinant of this linear transformation, trace of this linear transformation. Then at first I will tell, please at first think on self what you will do to solve this question, then see my solution. Okay, actually here I will see what is the matrix representation with respect to this linear transformation. Then we can tell easily this three option easily. What is the eigenvalue, what is the determinant, what is the trace. Okay, and this is the given linear transformation. For this, consider a arbitrary v which is 1 0 0 and consider the basis equal to set containing e1 e2 e3 where e1 equal to 1 0 0, e2 equal to 0 1 0 and e3 equal to 0 0 1. For this, consider one arbitrary vector. For easy calculation, take this vector. Then obviously v dotted v would be 1, e1 dotted v would be 1, also e2 dotted v would be 0, and this is equal to e3 dotted v. Then Te1 equal to e1 minus 2 times e1 dotted v times v dotted v times v. Now put the value. This value would be 1 0 0 minus 2 times 1 over 1. Here also 1 0 0. Then this value would be minus 1 comma 0 comma 0. That means I have got Te1 equal to this. Also we have to find T of E2, T of E3. For this, similarly T of E2 would be 0 1 0 and T of E3 would be 0 0 1. Then the matrix representation would be such type: minus 1 0 comma 0, 0 1 0 and 0 0 1. This is the matrix representation with respect to the basis vector E1, E2 and E3. Then by this matrix representation we can tell the eigenvalue of this linear transformation. Obviously the eigenvalue of this linear transformation is minus 1 1 1, and determinant, if we consider this matrix as A, and determinant of A would be obviously minus 1 and trace would be 1. Now let's see the option. Eigenvalue of T is plus 1 and minus 1. This is true. The determinant of T is minus 1. This is also true. And trace of T is plus 1. This is also true. And option 4 indicate T is distance preserving. For this, distance preserving, that means we have to prove d of tx comma ty equal to d of xy. This is the actual meaning of distance preserving. We all of us know. For this, just check oneself at first. D of t of x comma t of y equal to d of x comma y. This means actually d of tx comma ty whole square equal to norm of tx minus ty whole square. And by the property of norm, this means norm of t of x minus y whole square. And norm of t x minus y whole square means obviously t of x minus 1 y times t of x minus y. And by the property of distance, just put the value, and t of x minus y means x minus y minus 2 times x minus y dotted v over v dotted v times v times, here t of x minus y means x minus y minus 2 times x minus y dotted v over v dotted v times v. Now after calculating, this value would be norm of x minus y whole square minus 2 times x minus y dotted v over v dotted v times x minus y plus 4 times x minus y dotted v over v dotted v. And this would be omit. Then this would be norm of x minus y whole square. Have you understood? That means this is actually equal to d of x y whole square. Okay, that means d of tx comma ty whole square equal to d of x comma y whole square. So obviously our proof has done. This linear transformation actually distance preserving. That means option 4 is also right option. I hope my all viewers have understood this type of question easily. This is very basic, but very conceptual question. Okay? Oh well. Now I will see our goal of this lecture. I will see if V be a inner product space and Vi be a basis, then we always get a matrix A such that A is symmetric. Now I will see this concept, and this concept is very easy type concept, but I have defined this concept because I have told you inner product space is actually very important for not only competitive exam, for higher study. Consider V be a vector space and consider any arbitrary vector V is written as summation I equal to 1 to n xi vi, means any arbitrary vector written as combination of basis vector. Also consider another arbitrary vector w equal to summation j equal to 1 to n yj vj. This is written as any linear combination of basis vector. Then inner product v with w would be inner product summation I equal to 1 to n xi vi, comma summation j equal to 1 to n yj vj. And we can write this summation as summation ij, which is running from 1 to n inner product xi comma yj. Sorry, xi, since this is the scalar, just omit from inner product. This would be xi comma yj inner product vi comma vj. Then consider this inner product vi comma vj equal to aij, and notice here aij always equal to aji, and this is true for all I and j. Have you understood? Therefore, if we construct one matrix A which is equal to, whose index would be aij, obviously this is symmetric. Therefore, our proof has done. From a vector space V, we can construct always one symmetric matrix, combination of basis element. Okay? OL. Now I will define inner product in different way. Consider V equal to Rn. Then obviously dot product is defined as inner product x with y equal to x transpose y. Then you must know this is where x be the vector in Rn, then obviously x would be vector of n cross 1, then x transpose would be vector of 1 cross n, and y similarly y be the vector of Rn, means n cross 1, then x transpose y would be the vector of 1 cross n, 1. We all of us know the concept of dot product. We will define one new inner product by the concept of dot product. Consider one new inner product on Rn. Consider aij equal to inner product ei is, where ij belongs to n. Now consider x equal to xi ei, where I running from 1 to n, and y equal to summation j running from 1 to n yj ej. Then inner product x with y would be, this would be summation I equal to 1 to n xi ei and summation j running from 1 to n yj ej. And by previously this is equal to summation I comma j running from 1 to n xi yj and inner product ei comma ej. Okay, consider it inner product ei with ej equal to aij. So, and this is look like summation ij running from 1 to n aij xi yj. Okay, therefore there exists a nice observation. We can write this as dot product ax dotted with y, where A is the n cross n matrix which is aij and x is n cross 1 vector, then Ax would be Ax dotted y means obviously this is by property of dot product, this is Ax transpose y. So this is the matrix of type 1 cross n and this is the matrix of type n cross 1. So Ax transpose y would be actually 1 cross 1. Have you understood this concept? That means any inner product from any inner product, we can write inner product x with y equal to Ax transpose y. We can write this as x transpose A transpose y, and since the matrix is symmetric matrix, then that means actually x transpose ay. Just recall, in my previous video I have told you any inner product can be written as x transpose ay, which is actually Ax dotted y. And this property I have told you in my previous video, but today I have defined elaborately what is the idea actual, what is the actual concept. I hope my all viewers have understood clearly by today's video. Okay? Oh well. That means in Rn, always I will get one inner product which is look like Ax dotted y, where A be a symmetric matrix and A is actually inner product Ei with Ez. Have you understood this concept? I hope my all viewers have understood this concept easily. Okay? Oh well. Now I will see one nice observation. I have seen any inner product in Rn can be expressed as x transpose ay, and this is written as Ax dotted y. Obviously this is bilinear form, but my question is this always, if we can written as x transpose ay, is this always inner product? This is my question. At first check bilinear. For bilinear, this is very easy. If we consider x dashed, x double dashed, comma y, then we can write this as x dash plus x double dash, a with y. This is obviously x dashed ay plus x double dashed ay, and x dashed ay means obviously x dashed inner product x dashed y, and x double dashed ay means inner product x double dashed y. Similarly, x comma y dash plus y double dash, this is written as x comma y dash plus x comma y double dash. That means obviously this is an inner product space. That means xy map to x transpose ay, obviously this is bilinear form. But my question, is this inner product always? First thing, is this inner product? Xy map, when xy map to x transpose ay, is this inner product always? For this, recall x transpose ay. This is actually definition of quadratic form. All of us know, if A be 2 cross 2 matrix, which is symmetric, whose form is such type, then any quadratic form is written as A times x1 x2 plus A times x1 y2 plus x2 y1 plus b y1 y2. Have you understood this concept? We all of us know this is. Okay? Oh, yeah. And we all of us know any positive definite bilinear form always in inner product. Obviously this is bilinear form. This is not inner product. For this, consider this matrix A equal to 1 0 0 minus 1. And we have to, for positive definite we have to prove inner product V with V greater than equal to 0, and this is true for all V. And since, notice x transpose ay means this from A x1 x2 plus A is x1 y2 plus x2 y1 b plus b y1 y2. Here I have considered this matrix, so the value of A is 0. That means inner product V with V would be obviously a x square plus b y square, and consider arbitrary vector x equal to 0, y equal to 1. Then inner product v with v would be here 1.0 plus b, here the value of b is minus 1.1, this is equal to minus 1. Therefore, inner product v with itself, I have got this is equal to minus 1. So, xy mapped to x transpose ay, this is bilinear but not always inner product. Have you understood? I hope my all viewers have understood this process easily. That means all symmetric matrix not define inner product, and this is inner product when the matrix be positive definite. And what is the necessary condition of positive definite? If we consider this matrix, then always would be a greater than 0, b greater than 0, and determinant of the matrix always would be greater than 0. I hope my all viewers have understood why I have told you in my previous video positive definite, negative semi-definite. I hope my all viewers have understood this geometry in better way now. In my previous video, I have discussed the definition of positive definite matrix, positive semi-definite matrix, negative definite, negative semi-definite, indefinite matrix. But when a quadratic form is inner product, when this is the positive definite matrix, I hope my all viewers have understood this concept easily. Okay? Well, I will stop here. In my next video, I will discuss this type of question again, because this type of question and this type of concept actually very important for higher study. Okay? See you soon. Stay safe and stay positive always. And I wish again happy Saraswati Puja and happy Republic Day.